Hello everyone. In this video, we will learn about situational problems involving conics. To begin with, the general form of the second-degree equation in two variables is given as ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0, where a, b, and c should never be 0. Now, if you're given a second-degree equation, how will you know as to what conics it represents? So one way is we can make use of the discriminant, which is given as b squared minus 4ac, where b, that is the coefficient of the xy term, a is the coefficient of x squared term, while c is the coefficient of the y squared term. Now, if the computed discriminant value is lesser than 0, there are two possible cases. It could be the equation represents a circle or an ellipse. If the discriminant value is equal to 0, then therefore the equation represents a parabola. Now, if the discriminant is greater than 0, then therefore the equation represents a hyperbola. Now let's have an example. If this is the given equation, identify what conic it represents. With this, we can make use of the discriminant. In this case, there is no xy term, so we will have that as 0. Minus 4, our a is 4, and our c is 9. With this, negative 4 times 9, that would be negative 144, which is lesser than 0. In this case, this is an ellipse. Another example. Now, in this case, using the discriminant formula, there is no xy term, so that would be 0. Our a is 2, and our c is also 2. So negative 4 times 2 times 2, that would be negative 16, which is still lesser than 0. In this case, this is a circle. Now, how will we know if the equation represents a circle or an ellipse? So going back to circle, when you say a circle, the coefficients of x squared and y squared should be equal. Now, going back to example number 1, the coefficients here are 4 and 9. In number 2, it's 2 and 2. Another example. Now, in this case, making use of the discriminant formula, there is no xy term, so that would be 0 squared minus 4. Our a is 9, and our c is negative 4. So with this, negative 4 times 9 times negative 4, that would be positive 144, which is greater than 0. So in this case, this is a hyperbola. Another example. Now in this case, making use of the discriminant formula, still there is no xy term. Then we'll have negative 4. Our a is 0 because we have no x squared term. And our c is 4. So with this, negative 4 times 0 times 4, that would be 0. So, in this case, this is a parabola. Now, it is also possible to identify the kind of conics the graph represents by just simply inspecting it. So, if it is a circle, x squared and y squared should have the same coefficients, just like this example or sample equation. And the degenerate case is a point or nothing. Another, for a parabola, exactly one of x squared or y squared will appear. So just like this example. So in this case, it's x squared. For the second example, it's y squared term. So your degenerate case here, it could be a two parallel lines or a line or simply nothing or an empty set. For an ellipse, both x squared and y squared will appear. The only difference is that they have the same sign, but they are unequal. So just like this, 2x squared plus 5y squared. or it could be 4x squared and y squared. The degenerate case here is a point or an empty set. Hyperbola. For a hyperbola, both x squared and y squared appear, but they have different signs and at the same time, they are unequal. So, just like this, 5x squared minus 3y squared. Or it could be negative 4x squared plus y squared. The degenerate case here is two intersecting lines. Now, what do you mean by degenerate case or degenerate conics? For example, this is an equation of a circle in standard equation. The center here is positive 2 and negative 1. But take note, the radius is 0. So therefore, it's simply a point. So this is an example of a degenerate conics. There is a circle, but it's simply a point circle. Another example. This is still an equation of a circle. But take note, its radius, the r squared here is negative 4. So therefore, the degenerate case here is an empty set because you cannot identify its radius. Another example. This is an equation of an ellipse. But take note, it is equated to 0. So the degenerate case here is, it's simply a point. Another example. This is still an example of an ellipse, but take note, it is equated to negative 1. So with this, the degenerate case here is an empty set. And this one is an example of a hyperbola. But take note, it's equated to negative 1. When you sketch this, you will end up with basically two intersecting lines. Okay, now these are different equations and they are all non-degenerate. So meaning it really appears. So when you sketch this, you can really have its graph. So let's identify by simply inspection. So for number 1, we have x squared and we have y squared and it is subtracted. So with this is a hyperbola. Number 2. Take note in number 2, it's only y squared appeared. So in this case, this is a parabola. Next, for number 3, x squared and y squared appeared. They have equal coefficients and equal or the same signs. So with this is a circle. For number 4, it's only x squared that appeared. So with this, it is a parabola. For number 5, x squared and y squared appeared. They have the same signs, but they are unequal. We have 7 and we have 3. In this case, this is an ellipse. For number 6, x squared and y squared appeared, but it's negative 4 and positive 3. They are unequal, so therefore it is a hyperbola. State the type of conic section represented by the given equation, then sketch it. So, by inspection, it's only y squared that's given. So, therefore, this is a parabola. So, making use of the discriminant, so there's no xy terms, 0. Our a is 0 and our c is 1. So, indeed, it's 0. So, therefore, it's really a parabola. So, let's rewrite this to standard form. So, to do that, group all y terms, transfer x and constant to the other side. So, complete the square. So, half of 6 is 3. Square it, it's 9. So, add 9 to both sides. So, rewrite this to binomial form. So, that would be y minus 3 squared, 6x plus 24. In this case, factor out 6. So, this would be x plus 4. Or rewrite this in 4p form. So, we'll have 4, quantity 3 halves, then quantity x plus 4. So, let's identify its properties. So, the standard equation, it's already given. So, it's here. Then, the vertex is given as negative 4 and positive 3. In this case, this opens at the right. Okay, why? Because y is squared, and our latus rectum here, it is positive for p. So let's graph it. The vertex is located at -4 and +3. So take note, our p here is 3/2. So from here, count 1.5. So that's where the focus is. So count 1.5, going to the back, in order to get the directrix. So with this, it's 1.5 times 2, so that would be 3. So 3 up and 3 down. Connect it with a curve, so this will be a graph. Then our axis of symmetry, it passes through the vertex and of course the focus. So with this, the focus is located at -2.5 and 3. And the axis of symmetry is y equals 3, and the directrix is given as y, or x is equal to -5.5. Now let's have a sample problem. A parabolic shaped irrigation canal is 8 meters wide and 2 meters deep at the center. Write a defining equation for the parabolic shaped canal and determine its depth every meter. So take note, the given is it's 8 meters wide, so half of it would be 4 meters. So with that, another is it's 2 meters deep at the center. So therefore, the coordinate here would be 4 and 2, and of course at the center it's 0, 2. This is the vertex, and this is where our focus is. It opens upward, and our p is 2, so that would be x squared is equal to 8y, because it's 4 times 2, so therefore it's 8y. So this is our defining equation. And to get its depth every meter, so let's have x here from 0 to 4. So 0x, so that would be y0. If our x is 1, so our y is 1 over 8, or 0.125. If our x is 2, so that would be 4 divided by 8, that's 1/2 or 0.5. If our x is 3, so 3 squared is 9 over 8, to get y would be 1.125. And if our x is 4, so 16 divided by 8, we will end up with 2. Another. A road tunnel with a semi-elliptical arc has 16 meters wide base and 6 meters high altitude at the center. How close to either wall of the tunnel can a vehicle that is 2 meters high pass by the tunnel? So let's illustrate that one. So take note, the given, it's 6 meters wide base. So half of it would be 8 meters. So the coordinate at the end of the tunnel here would be 8 and 0. Another given, it's 6 meters high altitude. So therefore, at the top here would be 0 and 6. So 8 and 6. So the standard equation here would be x squared over 64 plus y squared over 36 is equal to 1. Take note. Another given is the vehicle is 2 meters high. So how wide would it be so that it can pass through the tunnel? So therefore, x is blank and the height is 2 meters. So using that, x2, and substituting in this standard equation, we will have x squared over 64. Our y is 2, so 2 squared is 36 equals 1. Transfer this to the other side, we will have this one. Or 4 over 36, that's basically 1 over 9. So transfer 64. Distribute 64 to the terms inside. So we will end up with this one. Get the square root of both sides. We will end up with 16 square root of 2 over 3, or that is approximately 7.54. So therefore, the vehicle should be approximately 7.54 meters from the center of the tunnel. So that's all about situational problems involving conics. Thank you.